So interference let's talk about the definition one more time. The definition is the phenomenon that occurs when two waves in the same medium interact. So the first thing that attracts my attention based on this definition is that we have two waves. So we're talking about two waves now that they are in the same medium. What's medium again? Medium is the area or the state or the space that the light or the wave is traveling through. For example, if light is traveling through air, air is the medium. If light is traveling through water, water is the medium. So if we have two separate waves inside one medium, then they will interact with each other. For example, what? For example, you have a water wave, and then you have another water wave. Okay, that's not a good drawing. Look, another water wave. And then maybe at some point, they hit each other. We call that an interaction. When they hit each other, there's so many different possibilities. They could hit each other on both to be on their maximum points. They could hit each other face to face right when they're in the maximum and minimum points. We're going to talk about all different kinds of interactions. But for now, interactions between two waves is when they hit each other, almost like in this point. And we're going to talk about what happens if these two waves hit each other in that point. Are they going to, for example, one thought or one guess could be, oh, they mix together and make a bigger wave. They become a stronger wave. Maybe that's why we in the ocean we have like bigger waves. Maybe there are smaller waves that they accumulate each other, and then they get bigger and bigger. Maybe smaller one gets together, they get medium waves gets together and make bigger waves. So maybe that's one of the reasons we may have big water waves in the ocean. So that's one thought. Another thought would be that maybe they hit each other and they like kind of like cancel each other, and the wave would disappear. That's another thought, and that's what we're going to talk about here. So generally, when we have two waves interacting with each other, few conditions may happen. So I'm going to just have these two waves like that. When they hit each other, okay, so we're talking about, I'm going to draw this water wave again here. When the water wave and another water wave, they come and they hit each other here. This is the time, and we're going to take a picture of this point where they hit each other, and we're bringing the scenario here. If they happen to hit each other in a way that the crest of the one wave, so when is the crest of the one wave here, happens to be hitting the other wave exactly on the crest as well. Okay, so this is one condition. Another condition would be a little bit different that we're going to talk about it next. Here is the other type of situation that may happen. One of the waves, again, like it's moving and has a crest at this point. Another wave is moving with a different kind of wave, and then it has its trough here. So in this case, both waves are meeting each other or interacting with each other at their maximum points. So remember, we're talking about this here. Another situation may arise that the maximum of one of them happen to be at the same place and same time and a minimum of the other. And in fact, in these two cases, we will have a two different outcome, two different results may happen. If they both happen to be in their maximum, or if they both happen to be in their positive side, maybe they're not exactly both in the maximum, but they're still in the positive side. We call this as a constructive interference. And when they happen to hit each other, one in the maximum, one in the minimum, we call it the destructive. Why is this called constructive interference? Because the resultant wave out of the two is going to be the bigger wave. It's going to accumulate and they're going to add each other up and construct a bigger wave because they're meeting each other both on the positive side. And if they happen to meet both in the maximum side, they will make the bigger, twice as big as the wave. Now, if they happen to meet each other in the second scenario, which is a destructive, they will actually at that point would be no wave. They will cancel each other out. If they hit each other at the opposite amplitude situation, or one of them to be like in rising, one of them to be in going down. So basically one crest or one trough, in other words, and then the destructive interference would happen, which may result in no wave. That's why if I don't know if you go on a boat on a wavy day, you see the waves on the water and you see all sort of interactions. The waves are coming from all different directions. They hit each other. Sometimes they make splashes. Sometimes they make bigger waves. And if you pay attention, sometimes there are places that there's no wave, even though practically would be impossible to have no wave in an ocean with all the waves coming from all millions of directions. So there must be waves. Then you see some parts that they're a little bit more calm, or it looks like the waves are interacting with each other, but they cancel each other out and make a smaller wave or a shorter wave. And if they happen to hit each other in an exact wavelength and an exact amplitude, one in maximum, one in negative, and minimal, you may result in a point that you see that the waves cancel, and then in that specific point and in that specific time, you result to have no wave. Okay, so one is constructive interference, one is destructive interference. Constructive interference is when you have two waves hitting each other at the point of maximum, and they build each other up and they make an even bigger wave. So if the height of the first wave is 1 meter and the height of the second wave is 2 meter, and they hit each other right into maximum, they will create a wave of a 3 meter. They will accumulate and they will add up to make a 3 meter wave. I'm talking about the height of the wave. Now, if they happen to hit each other when the first wave is into the crest and it's into the highest point, let's say 2 meter, and the other wave is happen to be in the trough, it's in the minimum, so -1, so it's going down. If they hit each other in that point, now the crest and the trough, or the maximum minimum, what happens is the destructive interference. Destructive interference is the resultant wave is not only is not going to be bigger, it's even going to be smaller because they're canceling each other. And if they cancel each other totally, you may even result in that point in a specific time no wave at all. Now, this may happen very rarely in water. But remember, we're talking and we're making examples of water waves and sometimes light rays just to understand the concept. At the end of all these conversations, we're making a conclusion that if water waves carry a property, and if we can assign that property to all waves, then we can conclude light rays should have the same properties, radio waves should have the same properties, and any kind of rays that we're talking about should carry and have the same properties. One of them is the destructive and constructive interference we just talked about. It's more feasible and it's more understandable if you instead of talking water waves, now let's talk about sound waves. Sound is another kind of wave. And if sound waves appear to have constructive or destructive interference, they follow the same rule, because this is a property of waves. Now, what does that mean? It means that imagine you have we have one speaker here. Now we're going to talk about sound waves, okay? So imagine we have one speaker here that is maybe like speaking and making some sound waves. Now, if that sound waves are coming with like rays, sound is also wave, so it's moving up and down just like that. If you have another speaker generating a different type of sound, now if they meet each other here and then you happen to also stand here, we want to check this, that if you have speaker number one and speaker number two playing at the same time, if they're playing at the same time, will you actually hear a louder noise or will you hear a lower noise? Now, the first guess would be obviously higher noise because you have two speakers, one coming from like here, speaker number one coming from speaker two. So obviously, if you have both of them on, you should hear a higher noise. But that's not the case. If they happen to interfere each other at the point that you're standing, if they to happen to create the destructive interference, they will actually cancel each other out. And this happens. If you have two speakers in the room, there will be places in the room that if you go and stand there, you will actually hear less noise or less sound. I mean, it's very difficult to get that set up exactly in a perfect orientation. But if you want it, you can try it. If you have two speakers, and then the only thing you need to be paying attention is to the waves that they're going to interfere. They're going to interfere in each other in a destructive manner. Because if they happen to interfere constructively or constructive interfere, you will hear a louder noise. You will experience a louder wave. They will construct a bigger wave. If they hit each other in a point that they are meeting at their maximum and minimum, or they're making a destructive interference, then you will hear a lower voice, a lower sound. Now, if they completely cancel each other out, which happens, that would be when, which is very rare, but you will have two speakers sounding very loudly in the room, but because you're in a specific part of the room, they actually cancel each other out and you hear nothing. Again, I should repeat that it's very rare to get that point because as soon as you turn on the speaker comes to your ear, but not only in one direction, because the sound goes also through the walls and gets reflected and come through your ears in so many different directions. So it's very difficult to find that setup that you have a specific point that all the rays all the sound waves distract each other. But there will be points in the room that you will go and you will hear a lower noise. If you have a surrounding sound system in the house, they're usually set up in a way that they don't create a destructive interference. But if you play around with them, you will notice interesting things. If you make the speakers closer to each other, or if you make in a certain way, you would see that the experience of the sound will be different. Sometimes it's even maybe a little louder, sometimes maybe even lower. And why is that happening? It's because of the interferences of the waves. So not only in the water we experience that, with sound we experience that, and then the next question will be, do we experience the same thing in light? Is it possible that you shoot two lasers in a very specific point, and the lasers and the interference in the light rays happen to have a destructive interference in that point? The answer is yes. You can do that. You can possibly create a situation with light rays to do the same thing and cancel each other out, and you will see a black point there, even if you shoot the two light rays in. But you have to have a very specific design. Remember, it's very difficult to get that design, but in the laboratory, it's not that difficult. There are devices and tools specifically designed for these purposes. And if you do conduct that experiment, you see that, light appears to not move in a way that we were expecting. It's not really going in a straight line. It's going as a wave. And then if I move the directions of the light, two sources of light, and play around with those, I see that there are they're getting dark points, even though there's light coming, but because they interfere with each other, they cancel each other out. Now I'm going to Yeah, it's very interesting, and I'm going to end this conversation with how can we experiment this with light? Because, like I mentioned, maybe with water, maybe with sound, you kind of like move the speaker around, you
Mhm.
play around with the frequency and the wavelength, and then you just kind of like maybe adjust it. But how do you do it with lights? So this is where interferences and the diffraction of waves come together as a conclusion. So one scientist wanted to discover how can we make an experiment to experience the constructive and destructive interferences, but with the use of light. Now, light is very difficult to get. You can't really like grab a piece of light or a ray of light. You can maybe like control it in some specific ways, reflected or refracted or like maybe misdirected. But how do you control it? There was a very interesting suggestion. So they said let's have a very strong screen where light can never pass through, and have a very strong source of light here, very strong source of light. Now the light is going coming from this direction, and this is a wall. This is a black screen which absorbs all the light and nothing goes through. And in this case, let's make one small opening. We talked about this in the diffraction properties of waves, and this is how they come in handy together. We're saying that if light is a ray and if it's a
Mhm.
wave format, it should follow the same form of wave, which meaning if you have and a small opening here, and if a light ray is coming, some of them are going to pass through this point, but they're not going to just pass through in a straight line. They're going to actually expand to different directions. Now,
Mhm.
which specific way is going to have this diffraction? We're going to maybe draw it this way. So I'm going to show the light rays again in our form of looking at it from the top, and these are the light rays coming. And as soon as they get it, they get diffracted, diffraction, and they get expanded this way. Correct? We talked about
Yeah.
this earlier as well.
Yeah.
Now, the question is, okay, let's make another opening here. That was the experiment that the scientist was working on. If I open another opening here, obviously I'm going to have some other lights going passing through. Now I'm going to have lights like that as well. Now this is where the light rays are going to interfere and hit each other. Now this
Mhm.
would be very interesting to watch what happens when the light rays hit each other at these points. This is what we're talking about. So maybe destructive or maybe constructive interferences is going to happen. We don't really know if light travels like wave, which was one of the biggest questions for years. Is light a wave?
Mhm.
If it works like a wave, it should have constructive and destructive interferences, just how we talked about here, just like sound waves or just like water waves. There should be points where waves hit each other in their maximum points, and
Mhm.
they happen to help each other to build a stronger wave, which is called the constructive. So both in water and sound, if that happens, you will hear louder sound and you will see a bigger wave. So if that's the case, in light, we should also see a brighter lights in at these points where they constructively interfere with each other. Remember, the lines represent the crests of the waves. So these are the
Mhm.
maximum points of the waves hitting each other. So at those points, we should see lighter, brighter points, and at the points that they look like to cancel each other, which are in the middle here, I'm going to show it as kind of like gray. We should see darker points, or maybe like just lack of light. Maybe if they completely actually cancel each other out, you would see that there are going to be brighter and darker points. So what actually happens is you have a curtain, a piece of like the wall, which is blocking the entire light, except these 2 points, and you're letting light to travel with through these very tiny points, and suddenly what you see on the other side is all these like bright points all over the place, which is the result of the constructive interferences of the waves, and you see like almost like kind of like stars, which you don't expect, because what was the initial expectation? Light travels in straight lines, like light would go straight line like this. Two
mm,
stray light of rays of light should travel through those small points and just go straight in a line, but that's not what's happening. And remember, these points, when we're talking about lights, these openings, we're talking about fractions of millimeter. Sometimes the points that we can't even see with bare eyes. So when you go to a laboratory and you do this experiment, I mean, if we ever get the devices together in one place, and you have to have a generator of light at one side. So this is where the light is going to be generated, and then you make the screen and you make 2 points, and then you will actually see the stars on the other side. Now, in order um, to spot them and to watch them, you need one more thing. You can't see light just in the air. You have to put another screen here. Like you put another uh, maybe wall or piece of paper or something, and then you can spot the lights, the pieces of the lights that are hitting at that specific port into that point. So you see the dots in there. So instead of seeing maybe one dot here and one dot here, which was the expectation, now you see all these little dots all over the paper.
mm.
And sometimes you see a brighter ones, sometimes you see in a smaller ones, but it's very different behavior. It's not a straight line at all. So that was again the beginning of talking about the diffraction, as well as the interferences, and how the result of diffraction of the light rays will result in interferences, sometimes constructive, sometimes destructive. And depending on the type of the light or the type of the wave we were talking about, either it's a water wave,
Mhm.
or sound wave, or even light rays, they all pretty much follow the same rule and same law, that if two light rays happen to meet each other, instead of meet, we say interfere. If two light rays or two waves happen to interfere each other, two possibilities are the extreme and the maximum of result, and the minimum of the result could happen. The extreme low and extreme high could happen. If they exactly meet each other at their maximum points, they help each other and they make a bigger wave. If it's a water wave, it's going to be a bigger wave. If it's sound wave, it's going to be louder noise. If it's light
Mm.
ray, it's going to be brighter noise, a brighter point.
Oh,
If they happen to meet each other or interfere with each other at their maximum and minimum points, if they interfere destructively, then they're going to cancel each other. And if it's water, it's going to be no wave. If it's sound, it's going to be no noise. And if it's light,
mm,
it's going to be dark points. So these are, as I said, they're the extreme low and extreme high. If they happen to happen in between, then you don't hear the loudest noise, but you don't hear the lower noise. You hear something in between. That's also possible, because
mhm,
not all the rays and all the waves happen to meet each other exactly at their maximum. So maybe one of them is in maximum, one of them is in midway. So they're still going to help each other to build a bigger wave, but if they are in the maximum, both of them, they would be the maximum wave that they can build. And that's usually how you want to design it if you're in a concert. Now, if you're in a concert and imagine you want the loudest possible music and sound to be played for your audience, I wouldn't assume that putting speakers in a concert is just as simple as going up the ceiling and installing there. There is a sound engineer and a mechanical engineer designing the room in a specific way that the audience will experience the loudest sound possible. I mean, if it's something we can do, why not doing it? I mean, I'm not saying that every auditorium and every concert place or every movie theater is equipped with the best sound surrounding system, but if they are, which I'm sure before the COVID we experienced different kinds of movie theater, and then sometimes you experience different sound, and then you're like, oh wow, that I just actually enjoy more watching the movie with this kind of sound as opposed to some other place maybe if they don't have the equipment to make the right installations of the speakers that make the constructive waves for the audience. So that's the conclusion of this topic, and it's a very interesting topic in terms of how waves have different properties. But a little bit more interesting than that is we discover the properties of waves with the use of one kind of waves, maybe water waves and sound waves, and then we discover that, and then we expand it to other kinds of waves as well. I mean, as soon as we find out that it's possible to make constructive waves and destructive interference, then we wanted to see, oh, how would that work in sound system? How would that work in light? And then how would that work in laser system? Laser basically is the same, sending lights, all of them making constructive interference. Imagine having millions of rays, all of them making constructive interference in a very specific point, and that's how we make lasers. So now laser is a whole entire world, right? So like, I mean, if you want to talk about surgeries, if you want to talk about transferring energy or like light, and so many different uses. So that's the conclusion of this topic, and that's the interesting part of it, and we can continue talking about it in the next session as well.